Okay, welcome back to the today's class. We will be seeing about losses, regulation, and efficiency of a transformer. Okay, losses present in a transformer. Okay, transformer is a static machine. There are no friction or windage loss or windage loss. Okay, if you see a motor, this motor will have friction while rotating. Each and everything which is rotating has a friction. Okay, but in a transformer is a static machine. It is not going to rotate anywhere or it is not going to move. Okay, so there is no friction. Or if a motor is considered, the motor has to rotate. While rotating, it has to withstand the wind. Okay, it has to push the wind out. Okay, wind out or in. Okay, anyhow, it should rotate in the presence of air. Okay, this air will be a resistant to the motor. Okay, so this is known as windage loss. Okay, there are two laws. One is friction loss and another one is windage loss, and these two losses are present in a motor, and these losses are known as mechanical losses. Okay, these are not electrical losses, these are mechanical losses because friction is mechanical. Windage loss is also mechanical. Okay, this is not electrical losses. Okay, but in case of transformer is not going to rotate anywhere, so there will be no friction or no windage loss. So hence the only losses occurring are core loss and copper loss. So in a transformer you can say the core loss and copper loss are being present. Core or iron loss, it includes both hysteresis loss and eddy current loss. Here what is hysteresis loss and what is eddy current loss we will see in detail. Okay. Because of the core flux in a transformer remains practically constant for all loads, hysteresis loss variation being 1 to 3 percentage from no load to full load. Okay, magnetic flux is going to pass through the core, that is the laminated core that you have made or present in the transformer. This core should be made up of silicon steel material. Okay, this silicon steel material has a loss known as hysteresis loss. Okay, what is hysteresis loss in terms of physics? You can say magnetizing a material and demagnetizing a material has a different curve forms. Okay, once you magnetize a material, the curve will be in a different form. Whereas you demagnetize the material, the curve for demagnetizing the material gets a different form. So while magnetizing as well as demagnetizing, the losses are different. This transformer loss is due to hysteresis loss. Here you can see about 1 to 3 percentage of the input power is due to hysteresis loss when the transformer is no load to full load. So if the transformer is no load, the transformer has a 1 percentage of hysteresis loss in its total input, whereas at full load, the transformer has 3 percentage of hysteresis loss in its total input. Next, the core loss is practically the same at all loads because the core is a constant. Why core is constant? You are not going to remove the core from the transformer. Okay, core is made at the starting time of the transformer, and the loss present in the core is always a constant. Hysteresis loss, the formula is WH. You can find it using efficiency B max 1.6, that is the power of 1.6. This is the maximum flux density of the core, and you should have a power of 1.6, and this one is frequency and this one is voltage. So when you apply this thing, and the output of this formula is in watt, and this formula will give you the how much amount of hysteresis loss is present in a transformer. Next one is eddy current loss, which is represented as WE. Here WH, here H represents hysteresis and in E represents eddy current. Here P is the power and B is the maximum flux density, and this is the square. You can see the power is in square, whereas the frequency is square, and T is the total time period the transformer is in on state. Okay, so this is having a unit of watt. Okay, These losses are minimized by using steel of high silicon content for the core and by using very thin laminations. So, core loss is due to the hysteresis curve. So, this hysteresis curve should be minimum. So, when you are searching the chemistry, you can see the material. You can see the material, that is the silicon content present in the steel. So this material has a very less hysteresis loss. So this material is chosen for the transformer core windings. Okay. uh, now you can see what is lamination. Here the lamination is for to avoid the eddy current. Okay. If a transformer is being loaded, the flux is going to pass through the core, and this flux is going to be alternating in nature. Okay. This flux will cut the transformer core. This flux is going to cut the transformer core. So a alternating current or alternating voltage is going to be induced in the transformer core due to the cut off flux. Okay. This induced EMF will be in such a way that it will tends to make a current in the transformer core, and this current is circulating in nature. Due to this, this current is known as eddy current. To avoid this eddy current, what you should do is you need to have laminations. We have discussed several topics about lamination from the starting of this class. Okay. You can see if you are having a very thin section of metal, then the eddy current loss is less. Whereas you have a different or several section of metals and are being in a very single solid state, then the eddy current loss is high. To make the eddy current loss minimum, solid metal is being cut into several pieces, and thin laminations are being made, and all these thin laminations are riveted together with the help of a rivet. Before arranging all the thin laminations together, after one and another one lamination, the surface should be insulated with the help of a mica or a paper or some other material should be used to insulate the two lamination, and all the thing is completely laminated. Okay. In the real time, the transformers are being laminated, laminations are being insulated using varnish. Next, you are going to see about copper loss. This loss is due to the ohmic resistance of the transformer winding. You know that all the materials such as copper, aluminum, gold, everything in the world has some amount of resistance present in the metal. Okay, metal has some resistance, and this metal resistance, when current is being passed, power is being dropped in the windings of the transformer or in the metal which is being the current is passed. So this drop in voltage while the current is passing through the coil or winding or a metal is known as copper loss. The total copper loss is, you can say, I1 square R1 plus I2 square R2. Here, why I1 square R1 and I2 square R2? Because you are having two windings. One is primary winding and other one is the secondary winding. You can see for the primary winding, the current flowing through is I1, and for the secondary winding, the current flowing is I2. Okay. Similarly, the resistance is R1 and R2. R1 is the resistance across the primary winding, and R2 is the resistance across the secondary winding. So the total copper loss will be I1 square R1 plus I2 square R2. Similarly, which is equivalent to I1 square R01 plus I2 square R02. Here, these two R01 and R02 are represented as a secondary state. Okay. When primary is considered, secondary is being given. If secondary is considered, primary is being given. Okay, this is not a problem. You just remember this thing. Okay, I1 square R1 plus I2 square R2. You need not to write this. Okay. It is clear that copper loss is proportional to current square or kVA square. Okay, you know that here you can see I1 square. So the copper loss is being proportional to current square, and it is being also proportional to kVA, the total volt ampere whole square. In other words, copper loss at half the full load is 1/4 of that at a full load. Okay, so the copper loss present here is half the full load, which will be equivalent to 1/4 of at the full load. This is the graph showing you the total losses present in the transformer. And you can see this is the transformer graph of a 75 kVA transformer, and the graph is for losses versus load. This is the percentage increase in load, and this is the losses in watts. These are the temperature rise, and this is the graph which is shown. When the load is being increased, you can see the total losses is being also increased. Okay, so when the load increases, losses increases, and for different temperature there will be different curves, because the metal resistance is also dependent on temperature. So only you are getting such things. Efficiency of a transformer. Efficiency of a transformer at a particular load and power factor is defined as the ratio of output divided by input. You all know things. Efficiency is nothing but output divided by input into 100%. Okay, this is the same for transformer also. Here you can see this is the output, and here input. Here input, you can see output plus losses is the input. So when you give power to the transformer primary, the output is from the secondary. Okay, once you get the output is due to input plus losses. Okay, input will be equivalent to output plus losses. So only you are getting the output. So you can see output will be present in the numerator, and in the denominator you know output is the same. And for losses, you know there are two loss. One is the copper loss and other one is the iron loss. And you can equate this thing into 1 minus losses divided by input. Condition for maximum efficiency of a transformer. Iron loss is equal to hysteresis loss plus eddy current loss. You know these things. So the maximum efficiency can be attained when the copper loss is equal to iron loss. So just remember this thing. So for maximum efficiency in a transformer is attained only when copper loss is equal to iron loss. So here you know the total iron loss, that is the core loss. Iron loss or core loss. Okay, iron loss or core loss is equal to hysteresis plus eddy current loss. You know WH plus WE. But when you consider when a transformer will give you the maximum efficiency, so the maximum efficiency of the transformer is attained at when copper loss is equal to iron loss. Okay, both the losses should be equal. At this time, the transformer is giving you a maximum efficiency. And this is the last topic, and this is the regulation of a transformer. Okay, what is meant by regulation? When a transformer is loaded with a constant primary voltage, the secondary voltage increases because of its internal resistance and a leakage reactance. So, when a transformer is being loaded, what happens here is the secondary voltage starts to decrease irrespective of the primary voltage. This decrease in secondary voltage is due to the losses present in the transformer core in the form of magnetizing loss, winding loss, copper loss, iron loss, core loss, etc. Okay, these losses will get some power drop, and so the voltage is being dropped in the secondary. Hence, to keep the output voltage constant, the primary voltage must be increased. So, the primary voltage should be increased to make the output voltage constant. You know that the output voltage is decreased irrespective of the primary voltage. To get the required output voltage, you need to increase the primary voltage and to subtract the loss. You should power up the loss to get the correct secondary voltage out. This rise in primary voltage required to maintain rated output voltage from no load to full load is expressed as percentage of rated primary voltage. This is given by the regulation of the transformer. So percentage regulation is equal to V1 dash minus V1 divided by V1 into 100 percentage. So you can say how much amount of primary voltage should be increased to get the correct secondary voltage is V1 dash. Okay, if you have V1 is equal to 100 volt and you get an output of 9 volt. Okay, the correct secondary voltage is 10 volt. Okay, so you need to give 11 volt to get the output of 10 volt. So this ratio, this increase in voltage is known as percentage regulation, and its formula is V1 dash minus V1 divided by V1 into 100 percentage. Okay, thank you.